Guys, welcome to another CEO Wisdom podcast, BCI edition. So, those that don't know, brain computer interface, which is a passion of mine. Got a special guest today, a very relevant one for this episode, Michael Witbrock. He is CEO at TransAxon. So, these guys are actually building the real thing, a la Neuralink, kind of. So, we're going to have a nice convo. Michael's in Auckland, New Zealand. Really special guy, kind of a mixed breed between a CEO and a scientist. And we're going to blow your brains out today because we're going to talk about some stuff that you think would be actual in 50 to 100 years, but this is actually existing technologies with proven studies and science behind it. So, Michael, welcome to the pods. Glad to have you here. Can you shortly introduce yourself and TransAxon?
So I'm Michael Witbrock. I am a professor of artificial intelligence actually at the University of Auckland, but I'm also CEO of TransAxon, and we are going to build brain-computer interfaces that everyone will want to grow. So our novel approach involves taking control of the processes which built your brain in the first place and have your brain decide to grow a 13th cranial nerve, a 13th nerve like the optic nerve or the spinal cord, but have that grow to a place just under your skin where it can communicate optically with a computer interface. And the reason we want to do this is that it's the only path that we can see to both full sensory resolution. So imagery that looks as real as the real world, and also tastes, smells, feels, proprioceptive inputs that feel as real as the real world. The other thing that it gives us is a plausible path to high resolution connections to systems like memory and cognition directly, so that we have a path to significant augmentation.
Interesting. I heard you mention that we think this is the best path moving forward. What about Neuralink, the approach that they're taking, and why do you think the TransAxon way could be potentially better or a quicker path to where you want to go?
Right, exactly. So there are two things that are kind of problems with most approaches to brain-computer interfaces, and somewhat unkindly, you might characterize them as either putting on a hat, right, and trying to work out from that hat what's going on in your brain, or poking holes into your brain, or sticking a bed of nails into your brain. I think that there's a little bit of an overstatement that's kind of true. So if you use an approach like infrared sensing, or EMG or EEG from the surface of the skull, there's no way you can get enough resolution to read signals out with high accuracy. And there is extremely unlikely to be a way of putting signals in from the outside of your skull electrically that significantly interact with brain activity. And there's also a potential problem of putting too much energy into your brain. So put aside the kind of HATS approaches. Neuralink and other similar approaches involve opening up your skull and poking a very large number of, well, in this case, sort of flexible, in the case of Neuralink, flexible polymer electrodes into your brain. There are two things that aren't ideal about that. If you put in enough of them to get anything like full visual resolution, for example, for sight, you're going to do an unbelievable amount of damage to your brain, right? It's very difficult to see that not having quite severe effects. The other is that there's just no way using these external electrode approaches to get high resolution connectivity into what are called subcortical structures, like the hippocampus in particular, which is probably needed for memory augmentation and ultimately doing things like possible downloads. Now, we don't actually know whether downloads are possible from a computer science point of view, right? Just viewing the brain as a neural network that you're trying to understand, it's not entirely clear that you can download those. But if it is possible, it's going to require much denser and much less damaging connections than the sorts of approach just people are taking it at the moment. And why our approach is very different is that it doesn't involve opening the skull at all, ultimately. And it, because it uses axons, right, actual neurons as its interface means, it doesn't have to damage the brain at all. Now, there is an interesting problem of integrating functions into an existing brain, but in terms of the sort of physical damage, because we use neurons, there's no reason why there should be any physical damage at all. You've gone silent.
Right, I was mute. Thank you for that. And it looks all very sci-fi to me, trying to imagine all of that. Can you explain it to us like we were five Feynman style of what would be the final product? Because me, I can picture some kind of UI on my arm or something in which I can control what's up there. Tell us about the final product and its actual use.
Right. And of course, you won't need a UI on your arm because you'll have a UI in your brain, right? Kind of the point of this is that you'll be able to control it with your mind directly. But so the final product will be something equivalent to a pill or a very small injection, which will contain a genetic program, right, which tells some non-neuron cells in your brain to become neurons and gives them what's called an axon guidance program, which tells them to build this new nerve track. Now, we don't know how to do all of those parts at the moment, but the process of, say, converting the cells is well not established in biology at the moment. So that can be done. Much of the science required to understand how to direct an axon has been done, but that's going to require significant research and development. And then at the other end, we're going to produce more neurons out of skin cells, which is actually the most common thing that people do now when they're trying to produce neurons. So it's kind of difficult to grow neurons from other neurons. So it's easier to convert other cells into neurons, which is what we're planning to do. These cells under the skin will be what's called optogenetically responsive. So when they fire, they'll produce light. When you shine the right sort of light on them, they'll fire. So they'll be able to be controlled by an optical, able to be controlled and to be read by an optical interface sitting on the surface of the skin. We kind of imagine it might be on the back of your neck or somewhere like that. And that will allow for the computer to interact with this nerve, which will provide very, very high bandwidth connection to the brain.
Right. Okay. So communicate with this nerve, and the cells, would they be fully biological? How would they be from the different cells in the brain? And would it be kind of a computerized cells vs non-computerized cells interacting together?
Yeah, so they would be, the cells will be fully biological, but they will have a different genetic program than the other cells in your brain, a slightly different one, and a different genetic program than other cells in your skin, right? As well as being neurons, but they'll be fully biological, and they will connect in exactly the same way to other neurons in your brain as the neurons in your brain already do. Yeah.
So would the device influence all of your cells, or just the the ones that we're trying to modify here, would it be like, oh, there would be some remaining human ones slash your own thoughts vs this BCI's
It won't.
thoughts?
It won't change any. It won't change any existing neurons at all. Right.
Okay.
It'll turn other cells which aren't neurons, which are replaceable, into neurons, and then those neurons will be part of the interface. And so all of your existing neurons will remain, and there will just be a kind of a new brain structure, right, that has grown that supplies this interface function.
Right. So it looks really less invasive than other approaches out there. Is that how you came up with the solution? Tried to make it at the less invasive possible? What did you factor in to create this strategy and this plan?
Yeah, so the two. So I've been thinking about this problem actually for a very long time, since the in 1980s actually, when I was doing an undergraduate degree in physiological psychology, which is a slightly odd thing for someone who ends up being a computer scientist doing AI to do. But and there was a good reason for that. But we don't need to talk about. I also did computer science at the same time, but yeah, I've been part of it is like just getting enough connections into the brain to understand it, right? That was the original motivation. So the first thing to optimize is how can I get the millions of new connections in required to get full resolution vision, for example. And then the secondary question. So how can I just put enough connections in without doing any damage? Right. That's the question. And then the second one was how can I do that without opening your skull, because you need a hole in your head, like you need a hole in your head, right? And other approaches require surgery. I don't think people will accept discretionary brain-computer interfaces, right, if it requires surgery and involves significant damage to existing neurons and doesn't give you full resolution and full function, right? The same sort of functions that you have from your existing neural structures. And if you think for a very long time about this, surprisingly, it took a while. You realize that neurons are the best possible way of connecting to other neurons in the brain, right? This is obvious once it occurs to you that other approaches are sort of more complicated and less natural. On the other hand, being able to do that does require neurobiology and genetics to have advanced to the point of the early to mid 21st century. Right? We simply wouldn't have been able to try to do this even 10 years ago, right? Things like the ability to turn other cells into neurons has only existed for a few years. The ability to get neurons to produce and respond to optical signals has only existed for well, in some form for a couple of decades, but it's only got very, very good recently. So we need to be at the technological point we are now to do what will end up being, well, a very complicated but also very simple thing, right? Just telling biology to do what it normally does in a slightly different way.
Right. And the skin level device, is it only for activation and deactivation purposes to always have the control over this, or tell us a bit more about that?
No. I mean, it's one thing to get millions of connections outside the brain. It's another thing to connect them to the internet, right? So connecting to the internet, having significant computation, storing, having a backup store for your memories, right?
Right.
Being able to access whatever the things which are going to come after GPT, right? Directly using your mind. All of that requires electronics, right? So you do
Yeah.
need to connect to electronics somewhere. We think the best place to connect to electronics is on the surface of your skin, where it's not going to do you any harm. Yeah,
Right.
you can take it off, for example, right? Yeah.
And how would the cells grow that much? Would they just like pack up more? Because it seems to me that there would be a problem of fitting that many new cells in a brain without disrupting it entirely. How, like, do they pack up tighter at some point? Like, how would that work?
Um, so fitting the nerve tract out and finding a path for it once you get to very high resolutions is going to be somewhat of a challenge, but not an insurmountable one. The actual cells shouldn't be a problem because remember, your brain has other cells than neurons in it, right? They perform support functions. We are going to be instructing them to turn into neurons. So the number of cells in your brain won't change, just the mixture of types of cells in your brain will change. So there shouldn't be a problem with too many cells. There will be more axons, right, than there were, and they do need to find a path. But we think that is a manageable problem.
And the RNA part, the gene expression part, it's not only at the start, but we could also tell them to modify themselves in different and more efficient pathways, I would guess, even after the initial setup is done.
If you think about the biology of this, and what is like, so just as a slight aside, I think in biology, it's very likely that we are at the point now that we were in the very early 1980s with the first microprocessors, right? That we now have techniques like AlphaFold to predict protein folding. We have techniques for predicting protein-protein interactions, and we have an increasingly good understanding of the genome. So my quite strong feeling is that we are at the beginning of a complete revolution in biology. And that means that if you think a little bit in the future about what kind of functions it will be possible to add to cells, right? There are a few limits to what you might be able to do. So in terms of providing the means to have persistent, for your mind to have persistent control over these new cells does seem possible in the long term. We're not aiming at anything but fairly normal neurons with making a connection to a different place than they normally would at first. But in the long term, there is a lot of potential for technological advancement in engineered neurons.
Right. Well, nothing's impossible. On the short term, I guess there would be memory limits and storage, and then you would decide what packets you want in, what kind of models, what kind of algorithm, what kind of update you want in your BCI. And it would be nice. I'm pretty sure that is already in your mind, but make it chat GPT like, like ask it like, hey, can you do this? Can you upgrade my software and so forth? Do you picture it that way? Very easy UX kind of?
I expect that ultimately these capabilities that BCIs that real BCIs add will seem as if they're just parts of your mind, right? It will become as natural to be able to remember something that's on the internet, right? Or to have added to your imagination a output from generative AI, or to calculate, to have the results of complicated calculations, right? As if you were just remembering things, or as if you were just adding 2 plus 2, right? It should be the case that getting the solution of a complex equation from something like Wolfram Alpha in your mind will feel exactly like getting the result of adding 2 plus 2, right? That just happens, right? I mean, instantly. So that is what the functions of your mind feel a certain way to you. There's no reason why new functions provided by computation shouldn't feel the same sort of way.
Right.
Now, of course, you can imagine a person inside your skull that you can talk to, right? You can do that now. You can make it. You can run a little Chat GPT thing on your brain at the moment and talk to it. So, by all means, if you want to do that, you'll get better at doing that. But I think that the experience can be far more natural than that.
Right. I feel we need to do a round two because there's so many other topics, AI safety, and your actual plan to building all of this. Because imagining and ideating is, yeah, it's not the easy part because getting great ideas and the right strategy to on what to execute is kind of a hard problem. So it's way harder than people think. But execution is so seems so complex in that sense. I'd love to talk to you about that. But let me finish up with one question. I think the round two, I'll just piece it up with that one. But what if I want it out? Like a lot of people would ask this. They love to have control, right? What if I want all of this out and I want to stop? It's how. What do you say to that?
Well, in the case of this, the simplest thing will be just to remove the interface, right, from the surface of your screen. You'll be able to turn it off anytime you
Like
want.
a
You'll be able
magnet,
to, exactly, like a magnet. Just lift it off, right? That's an important part of the control here. And so longer term, you could certainly engineer a system which would cause this cause the biological part of it to just stop functioning, right?
right?
I mean, again, that will require considerable work to do that safely, right? Because yeah, I don't want to speculate too much about that, but I can sort of imagine, I can easily imagine mechanisms for removing such a structure or causing that structure to remove itself.
Right. Or
But not
always give
working
more
at the
weight
moment.
to the natural human cells. I'm not sure how we could do that, but let's do round two because I mean, yeah, we're just scratching the surface here. Where can people find out more about you until then and TransAxon?
Well, we have a website, transaxon.bio, transaxon.bio. Um, uh, Go there. And if you're interested in helping us build this future, especially as an investor, do get in touch and we will send you some more material. Hoping to work with people.
Thank you, Mike.